I do teach glass blowing, but I do teach it with the perspective of teaching glass safety, because there's a lot of things that we've garnered over the years that are sort of true and sort of not true about glass. Number one, let me start out and say glass is inherently dangerous. You cannot make glass safe, but you can handle it safely, and you can create a safe environment for glass to be used. But that being said, if I can figure out how to use this, let's see how that looks. Well, I can't read that back there. The ancient Roman historian Pliny suggested that Phoenician merchants had made the first glass in the region of Syria around 5000 BC. But according to the archaeological evidence, the first man-made glass was in eastern Mesopotamia and Egypt around 3500 BC. And the first glass vessels were made about 1500 BC in Egypt and Mesopotamia. For the next 300 years, the glass industry was increased rapidly and then declined. In Mesopotamia, it was reviewed in the 700 BC, or revived in the 700 BCs, and in Egypt in the 500s. For the next 500 years, Egypt, Syria, and the other countries along the eastern coast of the Mediterranean Sea were centers for glass manufacturing. And the reason I say that is because one of the most exciting things I can remember as a kid was my mom and dad took me to Corning, New York. And there they have the Corning Glass Museum. If you've never been there, it's a fantastic trip because they will show you some of the ancient artifacts that have been collected over the years, as far as Egyptian glass, Bohemian glass. And what's amazing is the colors that they developed back then. They had reds, they had yellows, they had things that were optically pure. I'm not sure what that meant, but it meant that it basically transmitted light without any hindrance. They understood things 5,000 years ago that a lot of times we're catching up on. And there are many, many colors that have been lost over time as far as different types of glass. They just cannot be duplicated again. I think that glass is fascinating. I've always been interested in it. And when I had the opportunity to become a glass blower, I was like super excited. And I found out, oh my gosh, it's going to take me 7 years to become a journeyman. But that's the way they teach glass. It's like a guarded secret. They don't want to tell you how they do what they do. And so they incrementally show you something, and you're like, oh wow, I can do this. And after you've done it 1,000 times, you're ready to move on, and they're not ready for you to move on. That's kind of the way glass blowing has been taught through the years. And a lot of times it was passed down from father to son to the next generation and to the next generation. Nowadays, there has been a resurgence of glass blowing, and you can go to shops, watch people blowing glass. I think you can go to YouTube, and there's something like over 1,000 different videos that you can view of someone making some type of something out of glass. But for us today, I'm just going to talk about glass safety. Oh, here's some examples of some ancient glass. These were Egyptian. I specifically pulled out Egyptian artifacts. Some of this color, this particular color down here in the right-hand corner. Anyway, that particular color cannot be duplicated. But there are scientists and glass blowers working together to make colors that are almost as dazzling. But the particular measurement of that color has been lost in antiquity. And just for general definition, glass is a hard, brittle substance, transparent or translucent, made by fusing silicates with potash or soda, lime as a flux, and sometimes various metal oxides. Glasses have no definite melting point, but instead soften over a wide temperature range. Physical and chemical properties may vary greatly depending upon the formulation of the glass. Formulations of glass are very carefully guarded secrets, like Coca-Cola. You've got that formulation in a vault somewhere and they won't share it. Well, it's that way pretty much among glass companies when they come up with a different type of glass. Common glass formulations use quartz. Anybody ever heard that term before? A lot of people have. It's used extensively in the laboratory. What makes it unique is that it's almost 100% pure silica. And it's transparent to ultraviolet light. It has good mechanical strength, has a low coefficient of expansion. We'll talk more about that in just a little bit, how important that is. It's chemically inert, even when hot. It has a very high softening point. 1650C or 300F is the melting point. That's the point at which it begins to soften. You don't have to anneal it. Anybody familiar with the term annealing? Okay. Applications might be special chemical resistant glassware. Glassware is transparent to UV. It's used for cuvettes for infrared and other types of spectrometers. It also creates very precise optical flats. It can be ground and it can provide transparency, allow you to look into a reactor or something like that. Soft glass. Everybody's pretty much familiar with soft glasses. If you buy a glass from the department store to drink out of, it's pretty much made out of soft glass. And this is primarily silicone with soda, potash, or lime added as fluxes. More soluble. What they mean by that is it's less resistant to acids or less resistance to bases. Its softening point is about 700C or 129F. I don't like working soft glass because as I've gotten older, my reflexes have gotten slower. Yeah, that's true for some of you. But I will say this, it's really one of the most fun glasses to work in the shop. But you gotta be quick because when you hit the softening point, it's not very far away from the melting point. And if you're going like this, trying to make a piece of glassware or something like this, it just kind of runs away from you. And you have to get very quick. And my son's good at it, but I'm not so good at it. It has to be annealed very slowly. That's a key point with soft glasses. Lead glass or flake glass is composed of very little soda, and they use a lot of lead oxide in it. And what that does is it gives it optical brilliance, makes it nice and shiny. People like that. If you're drinking out of a nice goblet, that's lead crystal. It has a softening point of 626C, has a working point of 970C, and a lot of our canning jars and a lot of our jars in the laboratory are made out of leaded glassware. I tried my hand at being a neon glass blower one time. This guy kind of enticed me to do that. I'm glad I didn't stick with it because I wouldn't have had the nerves that it takes to be able to draw with a piece of molten glass. And you literally got this tube that's made out of leaded glass, and when you hit that melting point, when it begins to soften, you're almost there, but when it hits the melting point, you're taking a piece of tracing paper on an asbestos board or a transite board, and you're literally going like this to write your name as fast as you can, while keeping in a piece of tubing. It doesn't, you don't get to flatten it out. It has to stay a piece of tubing. And I got to admit, that's almost a skill and an art that I never really wanted to acquire. What we're most familiar with in the laboratory is Pyrex, Chemex, also called borosilicate glass. It has almost no soda or potash or lime. It has a substantial amount of boron oxide, about 12% by weight. It has a low coefficient of expansion, high chemical resistance, softening point of around 820C. working point of about 1220 C, and has to be annealed at 555 C or 1030 F. Now, this last figure, the strain point is 515 C. And if you look at the softening point and the strain point, there's about 300 degrees difference. And why is that important? Because anything above 515 C, the chances are really good that you're going to put strain into your glassware. So this is important for the rest of this discussion. It's used to make scientific glassware or kitchenware. There's a lot of stuff coming out of China that claims to be oven proof. Beware, most of it's not. If you take it and you move it from the oven and you set it on a cold surface, it tends to want to fall apart. And if you've never seen one explode spectacularly in the middle of your oven, it was from China and it wasn't oven proof.
I want to point out that all Pyrex made today is soda glass.
Yeah.
None of it's borosilicate. So old Pyrex was borosilicate, then chlorine sold off to China, and they cheapened the formula.
You are exactly right. So it's very hard to find the right Pyrex items. I lost a really nice measuring cup, and it said Pyrex on it, plain as day, and it was not Pyrex. As soon as I put it in the microwave, heated up a big stick of butter in there, you know, and I turned my back around and it was melted. Well, it continued to heat. Well, it was enough, and that thing fell apart in my microwave. It wasn't so much the heat from the microwaving, it was the butter itself transferring the heat. And for engineers, I thought, well, I had to have at least one slide in here that had some numbers on it, otherwise you might kick me completely out. And the coefficient of expansion is very important when you're working with glass because it really affects everything you do with glass. I'm not going to bother to explain the numbers. I'll leave that to you, and you can do that. But this gives you an example of the coefficient of expansion. I will tell you a funny story one time. There were some young engineers, I think I blame the engineering staff for this, and they made a big run of borosilicate pipe and forgot to account for the coefficient of expansion. And when they ran hot caustic through the pipe bowed up to the braces that were holding the pipe, and then another part of the pipe bowed down, so it looked like this. I had pictures of it for a long time, and I lost the pictures. But it was kind of cute because I think it's like over a run of about 24 feet, you've got almost a 3-inch increase in length. So you have to take it into account if you're putting pipe together. I did this, and this is a near miss that I turned in at work because I thought these were heat treated jars, but they're not. They're just simply lead glass jars that we use arbitrarily, and I poured some hot resin into it. Now, I had done it many times. I had poured hot resin into jars just like that over and over again. And this was the first time that I had ever had one where the bottom just dropped out of it. Now, the coefficient of expansion played a part in this. And then something called the shock factor played a part in this. And what happened next was the bottom fell out and I had a big mess to clean up. But let me explain what happened. The glass was cool because it was sitting in the hood, and it's at one temperature, all uniform. Glass does not like non-uniformity, okay? So it was there, all one uniform temperature. And when I poured that into it, that hot resin into it, it heated the bottom of it faster than the rest of the glass could account for the expansion. And it popped that bottom out, just as pretty as if I had scored it and broke it on purpose. So that's how you can absolutely overstress a piece of glass. Now, believe it or not, stress in glass is visible. And this hot-cold thermal shock is important even to a piece of Pyrex, because you can get away with heating up a piece of glass and cooling it down, heating it up and cooling it down, and heating it up and cooling it down. And you may not visibly see any change in that flask whatsoever. But I will show you eventually on a polarimeter exactly what molecular strain looks like. And it can build up over time. It's one of those things where it's good to send your glassware out and have it put in an oven and have it annealed periodically. I think that's a good maintenance thing for any laboratory to do with their glassware.
How often?
Well, I could say some arbitrary amount, 1 week, 2 months, because not all glassware is treated the same. And if you're tracking like a series of flasks in your lab, you might actually heat one differently than the next one. What's better is to simply have a schedule where you send things out to have them essentially de-stressed and do it on a regular basis. All your glassware should be in some type of rotation where you're sending it out and having it de-stressed. Mary Moore pretty much supplied my lab with the glassware that's in there. She would call me up and she'd say, hey, we got a lab closing down. You want to come get some glassware? And being a glass blower, I'm a natural glass hoarder. So I have lots of glassware in my lab. In fact, it's like a supermarket now. Everybody comes in and gets glassware. But the thing about it is, I don't know what's been in that glassware. I don't know how long it's been heated or cooled. So until I use a piece of glassware, I don't really ever examine it under a polarimeter, but it's my standard practice. If I take a piece of glassware for the first time and I'm using it, I put it under a polarimeter and I look to see whether or not there is molecular strain in that piece of glassware. Think of it this way. Here you've got a flask and you've got a joint stuck down into your flask. Very common thing to happen. And you take a heat gun and you're going around it. And it's one of those really good heat guns, that gets up to 1,000 degrees F. Well, you're at maximum temperature because you're in a hurry and you want to get it over with and you want to get that joint loose. So you're going around and around and around and around, and you're not thinking about the possibility of actually setting up strain in that side neck. And what happens next? Well, you have your unstuck joint, you send it out to cleaning, it comes back, and you don't think about it anymore. Well, what you might have done, I'm not going to say you do it every time, but what you might have done was set up a ring of strain right around the bottom of that joint where you were heating with that heat gun, and then, unexpectedly, in the middle of one of your cooks, all that tension that's in that molecular strain decides to release. And there goes your flask and whatever else is in there, and it's all over the place. You not only lost the flask, but you probably lost the heating mantle. And if there was a stir in there and it continues to whip around, the next thing you know, here goes your flask and your condensers and everything with it, right? Well, basically what I'm saying is strain is one of the things we don't account for in the laboratory, and we should probably do a better job of managing that. I do have an example of that so that you can see it, but right now we'll do something else. You've got to inspect glassware before you use it. I'm really amazed. You have people coming straight out of college, and they've been basically, maybe sitting under Dr. So-and-so, and they've done their thesis, they've got all their work generated, and they're ready to graduate. Well, they graduate, and then they come into a corporate setting like this, and it's amazing how many of them don't know how to be safe with laboratory glassware. It's just like, I've seen many, many times where a fresh PhD comes in, and he comes in and he starts grabbing glassware and he's ready to go and everything. Well, first thing I look over and I say, hey, where's your PPE? See, it's my standard practice that I have my PPE on whenever I handle any glassware. I wasn't going to start out the presentation with this, but I couldn't manage the clicker. So I put my PPE on before I pick up a piece of glassware, because remember what I said at the very beginning? Glass is inherently dangerous, but you can create an environment of safety where that glass is going to be safe to use. In fact, there's no better product for you to use in the laboratory to see your reactions and to see your experiments and things like this. But wear your PPE. These are cut resistance, A2, ANSEL approved, and I just don't, you probably, if you visit my lab, you won't see me without them on when I'm standing in the lab. Ground glass joints, one of my favorite subjects. Who here has stuck a glass joint? Okay, I'm going to tell you how to unstick a glass joint. Won't you be happy? First of all, don't get it stuck. Rule number one, don't get it stuck. Here's what you have to think in terms of glass joints. Cleanliness is next to godliness. Because a little tiny piece of something abrasive that can get in there and hang on to those ground surfaces is usually the culprit for your joint getting stuck to begin with. I have a nice flask here. I have a nice ground glass joint. You never put a ground glass joint inside of the other glass joint without some type of lubricant or some type of protectant between the two surfaces. In order to form a hermetic seal with a ground glass joint, say that 10 times real fast, okay, you have to have some type of lubricant on it. Well, okay, I don't want lubricant. I'm afraid the silicone's going to get into my reaction. It's going to cause me a problem. Guess what? We have something to actually help with that. It's called a Teflon sleeve. And we put the Teflon sleeve. This is a thick one, by the way, which you can order. And there you are. Simple fix. You don't have to have silicone. But let's say you're not bothered by silicone and it's not a problem. Okay? If you have this particular joint has a male end and a female end, okay? The female end has been properly greased. If you look at this, it's nearly clear, okay? That is a properly greased joint. Now you can over-grease a joint, of course, and have stuff run down in the inside of your flask, which is a common mistake, but you'll learn not to do it after you've done it about 3 or 4 times. And you learn how to do this. This is not lubricated. And some people, I've walked in the lab and seen where the joint itself is only partially lubricated. And they think, oh, well, a little lubrication goes a long ways. No, you need to lubricate it from top to bottom. And when you put the pieces together, you give it a little twist, not much, just a little twist to make sure you have the coating evenly spread inside. And that's how you make a good hermetic seal. High vacuum, you can get high vacuums. You can actually, a flask can actually accommodate about 15 pounds per square inch of pressure without any real problems. And ultra high vacuums are capable because of the spherical shape of the flask itself. But I use Dow just for advertisement. This is high vacuum grease. And I put just a little dab will do you. Anybody remembers the Burl Cream commercial? I'm showing my age here. And here are some thin sleeves that can be used to actually put between those joints. If you don't want to use silicone, you can use these thin sleeves as well. Now you might say, why is all this important? Well, if you're going to work in the lab, you need these little techniques and these little things to prevent you from having some other serious problems. Because if you never have to put a heat gun on your joints, you're never going to set up molecular strain, right? How am I doing on time? Y'all aren't sleeping yet. Okay, next thing I want to talk about, one of the most common mistakes that I've seen actually done. I actually witnessed it for myself, could not stop a new employee from doing it in time, and they lost the leader to their thumb. Okay, remember, glass doesn't like uneven twisting or strain or anything like this. And what she was doing was trying to put a piece of tubing in a stopper. And a lot of accidents occur while they do something that sounds so simple, right? Stopper with a hole in it. Finding a piece of glass tubing that will fit nearly the size of the hole, okay? She was going like this. She thought she was being safe because she had her hand away from the first part she thought would break. So she started pushing this in, and I actually turned around about then and saw her trying to push that into that stopper. And what happened next sent her to the hospital. And Dr. Mize could not catch the leader in time, so she left Eastman with a thumb that just would not work. When you're going to insert a piece of glass tubing into a stopper or even an adapter, like an O-ring adapter, you know, that has one of the twist tops, hold it about that far away, work it in. It's okay to twist it at this point because it's not going to break. If you're holding it out here and you're going like this, then there's too many forces working against you. Always wear your PPE, your cut-proof or cut-resistant gloves, and you work it in by gentle twisting, and then you have whatever kind of apparatus or device you need. But I will tell you, this is a very common accident. Another good common accident. Everybody know what a Dean Stark trap is? There was an accident here at Eastman where someone had a Dean Stark trap break. And Dean Stark traps, I don't have one with me today, but they have a sidearm on them, and they were using the sidearm to try to unstick the joint. And all they had to do was snap that, which is exactly what happened, and then they were exposed to whatever they were working with, plus the risk of being cut was very high. I can't remember in the near miss whether that was a cut incident. I don't think it was, but
it wasn't an injury.
It wasn't an injury, was it? All right. Let's see here. Got that one covered.
So how do you unstick the ground glass?
Oh, you want to know? You want to hear the glass blower's remedy? The Chinese water torture test. Ah, you laughed.
I did.
Literally, I have done about 3 different things to try to unstop a joint. But I put a glass joint that was stuck into a sink and started a very, very slow drip of water on that. And in about a day or 2, that joint will come apart.
Wow.
It works. The other trick is to put it into some type of a vessel where you can carbonate the water. And after a while, the bubbles or the gas will migrate in between the joints and force the joints apart. If you're a glass blower, it's not broken if you can fix it. So, the old tried and true method is to take the back end of a brush and start going quack, 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 and eventually it falls out. Or it breaks, and you fix it. Now that's what they won't tell you that they do at Lab Glass, but that's exactly what they do at Lab Glass because that's what I did. So the other way, of course, is don't get the joint stuck to begin with. Make sure you have proper lubrication in place when you're putting the two pieces together. And if you give it that little twist and you feel something grind, stop, pull it apart right quick if you still can. And then get in there and wipe that out. Apply fresh stopcock grease and then put it back together. Okay? That's my answer. And the Chinese water torture test really works. That's what's amazing. But tricks old glass blowers know, you know. So anyway, that being said, let's see here. We covered that. What else have I got? Was that the last one? I guess it was. Yep, I think it was the last slide. Okay, now I have brought with me a little piece of tubing. Every now and then there's a need to shorten a piece of tubing or something like this. And we go back to this coefficient of expansion, surface tension. All of these things are very important in working with glass. All glass needs is a place to break at. To do a controlled break, you have to have a point at which the glass will break that you desire for it to break at. Now remember, glass breaks, so you tell it where you want it to break. This is a tungsten carbide 4-sided knife that is used to actually score glass with. And you can place your thumb safely over the top of it like this and score it, okay? And there's a little tiny scratch there. And without that scratch or that release point, I can bend this all day, but only so far. Because after that, it's just going to fly into about 2 or 3 pieces. But by having that little tiny scratch on there, apply a little moisture. Capillary action pulls the moisture into it and actually begins the breaking process for you. It pulls apart, nice square edge, and you take a piece of emery paper to that, and you're ready to go. Right? See, isn't that cool? I actually pull it, but there's a natural force in your elbows. When you pull something, it automatically does that. So it could be a combination of both. I can't really tell you which. I can break up to a reasonably about a 1-inch piece of tubing without much fear of breaking it any other way. And it takes a little skill, and you can break up to about a 1-inch piece of tubing. I wouldn't try anything more than that because it's a whole lot easier to take it down to lab glass and have them saw it in half. Anything bigger than that. Okay. When you're handling glassware in the laboratory, your PPE is your first line of defense. That's why when you're handling glass, doing assembly of different pieces of glassware so that you have a desired apparatus for a reaction of some type, you cannot minimize having these gloves on because they will prevent an accident to you, right? Okay, that's what I've got today. Anybody got any questions? More questions?
How's your polarizer work?
Well, that's
Could
an
you
interesting
repeat the
thing.
question?
I want you to be able to see the molecular strain, and it's really the only way to see it with the naked eye. And what I have is a piece of glass that I worked in my shop, and it's what we call heavy wall. It's about a 3-inch OD, and so it's going to show the strain pretty vividly. That's the reason I brought this particular piece. And what you'll see is this end, which has no flame work actually taking place back here. And then this end, which I rolled up, I was in the process of making a really nice vase, and the strain is about right here. And what's interesting is I can actually heat that up to the annealing point, and all that strain will go away. But I deliberately left it here so that you could see it for yourselves. So at this point, if you want to come up and see some strain.
Before we do that, I have one question for you. What sort of glassware safety tips do you have for the home? What should we be doing at our houses that we're not?
Sure. Like for instance, a glass cake pan. Realize that most of the glass that you're going to be able to buy at Walmart or someplace like this is just what's called heat treated glass. And it's been taken up to a specific temperature, and then they ramp it down very slowly, as that to the manufacturer is enough to call it oven proof. Because up to that point of about 550 degrees, the glassware itself is going to be stable. But if you go beyond that, there's a real good chance that the piece of glassware is going to break. And so you have to treat glassware in the home, whether it's a Pyrex measuring cup or whether it's a cake pan or something like this, you will have to treat it with suspicion. And if you don't, then you'll get the joy of cleaning up the mess. I haven't done it in a while, but I do remember breaking a glass dish in the oven, and it was pretty unpleasant cleaning it up. Another thing you don't do with glassware in your kitchen is heat it up and then get it out of your oven and set it on a cold surface. Everybody loves these granite countertops. And you just pull that thing out of the oven. You know you're not going to hurt your granite, but you set that piece of glassware down on top of that cold surface. There's a really good chance you're not going home with your bakeware. It is going to fly in about 20, 30. I swear there wasn't a piece that big I was cleaning out of my oven that was that big. So it can be pretty exciting when that happens. Anybody remember Corel?
Oh yeah.
Oh, that was the glassware from hell. I mean, if you've never seen Corel explode, they had dishes that just sat in the shelf. And the way they made this supposedly unbreakable was it was surface treated just like tempered glass. When the spun glass that they were using to make the actual plate from came out of the end of the furnace where it was still sort of at annealing temperature, they would hit it with a blast of cold air. Okay? Anybody ever been to the glass plant and seen them make tempered glass before? Mm-hmm. It's really exciting when they take the bowling ball and drop on it, right? Well, and then you take one little tiny corner and snip it with a pair of pliers and the whole sheet just explodes in front of you. I mean, it's quite dramatic. Well, unfortunately, you can't buy that glassware anymore for your home because they got sued a lot. And it was because when this stuff explodes, it produces needle-like shards of glass. And they were very, very sharp, and many people got cut. So I'd say as far as safety in the home, know what you're working with. Be prepared. Hot pan pads for sure. But put something under that glass and do not put it on a cold surface if you've heated it up. Any other questions?
So if we have those Corel plates, which are not in fact unbreakable, because I've broken Corel bowls,
Exactly.
what should we do with them?
Buy new ones. I really did. I had a whole set, 8-place setting, and they were thin and light and looked great, and very easy to take care of in the dishwasher and stuff like that. Man, first time I broke one and saw the way that thing broke, I said, nah, I don't think I want these, because it was like needle-like shards. You remember when the bowl broke? Did you see any needle-like pieces?
I did.
I mean, it's just like long shards of needles, and they fly everywhere, fly all over the place. So yeah, I've got new stoneware.
So are there any hazards in ceramics and stoneware, or that stuff is pretty much lifetime?
Different set of coefficient of expansion. The thing doesn't expand. If you look, if we were to put that table back up there again, if you look at the expansion rate of concrete, which is, I guess, a ceramic equivalent, it just doesn't expand the same way. So you're not likely to lose stoneware by thermal expansion or contraction. Any other questions?
Can you induce strain just mechanically?
Oh, yes, you can. I took a flask one time, and I was setting it up in my lathe at Lab Glass, back when I worked at Lab Glass. And rather than getting it chucked in there properly in the lathe, I was going to put side necks on it. It fell out of my lathe. So this is a blank. And it fell out of my lathe and hit a concrete floor and bounced like a rubber ball. And I'm like, wow, that's amazing, you know? Then it just occurred to me, you know what, you ought to go see if there's any strain in that before you heat that thing up. Well, I took it over to the polarimeter that we had, stuck it under there. That thing was full of strain. Everywhere it had hit the floor, it had put strain in it. So energy in, broken glass out. That's about the best way to say it. Any other questions?
So what do you make in your shop for it's now a hobby?
No, right now it's Christmas ornaments.
And they're very beautiful, I can tell you.
Yes, these guys set of them, of which I still owe you one. I haven't forgotten. But anyway, it's I know that like we store glassware in a drawer. That's what I do in my lab. Try to put something between the flasks because if you pull the drawer out, they're going to go clink. And it goes back to the scenario where it fell out of my lathe. Believe it or not, that flask did not break. That just blew my mind. Because it fell about 4 feet and hit the floor and bounced. But it was full of strain. Any other questions?
So glass is stronger in compression than in tension, right? So I guess that's the question. I've always heard you're better if you're squeezing it than if you're pulling it. If you're pulling it.
Exactly. And there's a formula. There's actually some formulas out there that you can go see that will tell you the thickness of the glass and things like this and how much vacuum you can pull on it and or how much pressure you can put on it. As a rule of thumb, 15 pounds per square inch is what I was always taught that you could apply to a round bottom flask without fear of it going up in smoke. Still not a good idea to put pressure on glass. You can help it. Any other questions? All right.
That's usually connoted on the glassware, correct, Doug? Like vacuum rated glassware versus your normal run of the mill, like, oh, I'm just fixing something up, right?
Yeah.
I know we've ran into that before with certain near misses here and there. You know, a person used glassware but it's not vacuum rated.
I'll be honest with you, I've seen very little vacuum rated glassware. And I think that would be considered to be specialty glass because almost all the glass that I have in my laboratory and most of the laboratories that I've seen are not vacuum rated. But I can tell you that if you're pulling a vacuum on something and you've inspected the glassware carefully, below 1 torr is capable without any problems. But if you see what I'm saying? I mean, you're right. That was a good explanation. It's almost all shape dependent when it comes to vacuum. Like if you got an Erlenmeyer flask and you're going to pull a vacuum on it, well, triangle's the second strongest shape theoretically. But remember that flat bottom that's on the bottom of the Erlenmeyer? Check it for strain because it's usually something that gets heated up and set down on a cold surface. And that would be more likely to fail than a round bottom flask. Anybody else?
So it seems like vacuum is the way to go, right? It's 15 pounds per square inch, right? Where normal is 14.7. So I can pull full vacuum on this puppy, but I don't want to put a lot of pressure.
No.
Right?
You got it. You got it. It's vacuum's not the problem.
Yeah, pressure.
Yeah. Anybody else? I'm just dying to show you this. I've been waiting all day. This is like the cherry on top right here. You've waited to get to this point. So anyway, anybody want to come up and see some strain? Real strain. And here is the piece of glass, unheated. There's been no heat applied to this end.
Right.
You see, and this end was heated up to molten and then allowed to cool without any annealing.